In this lecture, we will continue our discussion on learning paradigms. So far, in the self-supervised learning, we have talked about some pretext tasks based self-supervised learning. Today, we will discuss about contrastive learning. The goal of contrastive representation learning is to learn such an embedding space in which the similar sample pairs stay close to each other while the dissimilar ones are far apart. Think about this. Is it a necessity that contrastive learning has to be only in the unsupervised setting? The answer is no. Contrastive learning can be pretty much also in the supervised setting, though more in the interest of our own lecture, we will be discussing more in the unsupervised or self-supervised setting. So to understand the contrastive learning, or why is it called contrastive, think of this triplet where we have this x, plus, which is a sample similar to x. Also, we have x minus, which is a sample dissimilar to x. So if we are provided with this triplet, how would we imagine this triplet in a feature space? Let us think a moment about this. The answer would be somewhat like this, that in the feature space, if we have fx here, the fx plus may be somewhere here that is quite close to each other, whereas we would probably expect the fx minus to be somewhat further apart, right? Now, before proceeding further, it's also very important to understand that when we are saying that these samples are related or are similar, or these samples are unrelated or dissimilar, this somewhat depends on our own definition of what is related, what is unrelated. Before diving into the contrastive SSL methods, we would like to discuss about potential generation mechanisms of positive and negative samples. Of course, if we are talking about supervised setting, this problem becomes trivial. How? Because in the supervised setting, you are given a data set with the corresponding annotations, right? In that case, for sure, you can, let's say, sample one data point or one image from a particular class, another data point or another image from the same class, and they are the positive pair, and then yet another data point or image from a different class. However, this is not anymore that trivial when we are working in the unsupervised setting. Why not? Because in the unsupervised setting, we don't have the annotations, right? If we had, of course, we are then working in the supervised setting. Without the annotations, how do we say that, okay, this particular data, they are related and this one is not related? Let us think a bit about this. Before moving to the next slides, maybe you can take a pause for a few seconds and think about this. Try to think about some ideas which would probably work, and then you can verify with the existing ideas. Okay, so from the domain of computer vision, one very straightforward idea is to sample patches from an image. That is, let's say you were given 224 cross 224 image. For the sake of our contrastive SSL, we are, let's say, rather working with 112 cross 112 images. We can sample 112 cross 112 patches from the original 224 cross 224 image. Of course, even if we are working actually with just 224 cross 224 image also, we need to just upsample this 112 cross 112 patches to 224 cross 224 before feeding to the network, right? Now think about this. In general, so this is a general assumption, not necessarily it holds 100% of the time, but mostly it holds, and that's what matters. That if two patches are from the same image, they're expected to be related, they're expected to be similar or like representing similar concept. Whereas patches from a different image probably, again I emphasize the word probably, represent more dissimilar concept. This idea was proposed in computer vision. Think about this, how it would be applicable in earth observation, how much it would be effective for the very high resolution images, how much it would be effective for, let's say, 10 meter per pixel images, and how much it would be, let's say, if we go coarser like 30 meter, 100 meter per pixel. So another similar concept that is adopted in the earth observation, it's very similar to our concept of sample patches from the same image, is based on the first law of geography, which says everything is related to everything else, but the near things are more related than the distant things. To visualize this, wherever you are sitting, think about that particular location. And now think about your neighborhood. Let's say you are sitting in a particular type of building, right? In your neighborhood, probably the buildings look quite similar. You go further apart and probably you face more and more other geographic classes, earth observation classes. Like, let's say you go further apart, probably you run into agricultural area, probably into a forest. Whereas, let's say you are right now actually sitting in a forest when watching this video, and for kilometers around you, you are probably surrounded by forest, right? So this brings us to this principle that, okay, everything is related to everything else, whereas the near things are more related and compared to the distant things. So similarly, we can also construct a temporal concept of near, how near the images are, how for a given location you can think of the successive images as positive pairs. So this is again also a bit related to the discussion we had with respect to the video in the last lecture. So what's happening is that generally there is a temporal progression, and today's image will be related to the next acquisition, let's say after 5 days, whereas it will be less related to the acquisition, let's say after 50 days or after 100 days. This concept can be used to temporally sample positive pairs or negative pairs. So at this point, I would like to quickly touch upon this contrastive multi-sensor self-supervised learning approach from the paper that has been cited below. So this particular work, the idea is to bring the optical and the SAR patches in a similar feature domain. So when doing so, what has been done is given a collection of the optical patches and its paired SAR patches. From these paired SAR patches, it's very easy to get also the unpaired SAR patches. How? We just need to shuffle these particular patches. So let's say we have this ABCD and we also have the paired SAR patches ABCD, and we just shuffle, and now we have this B here, which doesn't, the B SAR patch doesn't of course pair with the A optical patch, right? So now the task could be to actually make the A optical patch and the A SAR patch, bring them closer in the feature domain, whereas A optical patch and the B SAR patch, right, to push them apart in the feature domain. Okay, so far we have got the basic idea of what is contrastive learning. We have also discussed how would one possibly generate positive negative pairs in such unsupervised setting. Of course, there are more ways as well. However, we have discussed a few mechanisms of doing so. Now, let us try to understand a bit more about the algorithm behind contrastive learning. So a common contrastive learning framework, which is applicable for not just one, rather various contrastive learning approaches, would be to have an image and a transformed version of it, and both of them are processed by a model, and to have the similar feature representation for both of them, while of course for another image which is not related, to have a dissimilar feature representation. So how can we achieve this? Let us try to understand this in a bit more details. To discuss the learning algorithm of SimCLR, one of the popular and early contrastive learning, self-supervised contrastive learning approach, let us first think about what all would be the inputs to SimCLR algorithm. The inputs would be two networks, a set of augmentation functions, a particular batch size, and there would also be some input or inputs regarding the loss function, which at this moment is not so important for us to understand. However, we will mention also them briefly later. Okay, now based on these inputs that we have, let us think how would we use them to design a contrastive self-supervised learning approach. So given the training batch of the images x1, x2, xn, let's say, what would we do? Pick any image from this batch, let's say the image xi. We'll follow a number of steps for this image xi. What are those steps? We would sample two random augmentations, let's say t and t dash, from a, let's say, like it is available to us, a family of possible augmentations, and thus we would generate two transformed images. So now what? Given that we have generated two transformed images, we would pass them through if. What is if? Remember, we talked about having two networks, right? So if is one of them, and then we will again pass them through G. So we talked about two networks, F and G. So both transformed images, the positive pair, we can call them, they are passed through F and G. So let us look at these operations in a bit more mathematical or equation perspective. Given the xi, first time we processed it using T transformation, then processed it with F, and then with G. And let's say we got this Zi1, and for the next time we processed this xi using this T dash then through F, and then through G, and we got Zi too. So remember, where did we start? We started with n samples, right? Our batch size was n. We had this x1, x2, xn. And we are doing this for each xi, which means for the batch size of n, what are we going to get? We are going to get 2n feature vectors. Now, think about like this. For any two of these projected features, ZA and ZB, we can compute, let's say, cosine similarity, and let's call this SIM, SIM, ZA, comma ZB. Now, considering a positive pair ZI, comma ZZ, we can compute for these pairs I and J, basically a loss term small l, okay, which is taking this similarity between this Zi and Zz. So these are the positive pairs, and also in the denominator you see it's taking the similarities for all these 2n samples except the I sample itself. So this loss function, this will indeed push these positive pairs in the feature space closer, whereas pushing the negative pairs further. Also, in the loss function, we see this particular term tau, which is, if you remember, that there are some also inputs we said in the algorithm related to the loss function. So this is one of those input. It's called temperature parameter. Now, this L ij is one positive pair. We can similarly compute this small l term for other positive pairs, and we can average across all such positive pairs, and we will get our loss term capital L. Now, let us try to quickly discuss some results related to the SimCLR itself. We are at this point not interested in exact numbers of the results. We are rather interested in some of the properties exhibited in these results rather than those exact numbers. So what are those properties? So one of the aspect related to result or related to the algorithm itself, we have seen in the algorithm that augmentation is a very important part of the algorithm, right? And we remember again the principle that we said that pretext talks in the self-supervised learning, they need to be challenging. If the pretext talks are not challenging, then the self-supervised learning would not work well. So what one could do is, one can, so we talked about this T and the T dash. This T or T dash then can be instead of being just a particular type of data augmentation, they can be composition of augmentations. That is, let's say given an image, you crop it and you rotate it, right? So these are two different augmentation. It can be a composition, such composition. And there are, if you think about these possible augmentations, we have not listed such possible augmentations here. I encourage you to research a bit about this. What are possible data augmentations that is possible, and this is something very important. It's used in a lot of different settings. And one very important aspect here to understand is that the augmentation often works in spatial domain, like crop, rotate. There are augmentations also which rather work in the spectral domain, like image blur or Sobel filtering. Now, what happens is that if you take a composition of augmentation from the spatial and the spectral domain, let's say you take a crop and you apply Sobel filtering on the top of this, this would be generally be considered a more challenging augmentation rather than taking a composition of augmentation from the spatial domain only or composition from the spectral domain only. Why so? Because such a composition is taking care or making the task difficult in two different ways, right? Both in the spatial manner and also in the spectral manner. That is the reason that such data augmentation composition is more challenging and thus works better in the context of SimCLR. One obvious point that I would like to mention is that stronger data augmentation is needed in the case of SimCLR in comparison to the supervised learning. In a way, the data augmentation in the case of supervised learning, this is more optional, right? Whereas in this case, SimCLR, this is not any more an option. This is a part of the algorithm itself. So stronger data augmentation is required in this particular case. One very interesting property that was shown in the original SimCLR paper is that the SimCLR could benefit from the bigger models, or the performance scales somewhat with respect to the model size. And this is a very important property which will also come back again in future, especially when we talk about vision transformers, because if the model size is increased, we add more layers to the model, and indeed the performance doesn't increase, then there is no point in rather increasing the model size, right? This aspect we have also briefly mentioned when we have discussed residual network, ResNet, right? So this is a very interesting aspect of SimCLR, or rather of contrastive self-supervised learning, that they scale somewhat with respect to the model size. We will discuss about this further in our next lecture. Thank you.